So welcome, thank you for coming. I'm David Olsen. I work on the PGI compiler team at NVIDIA, and I'm here to talk about parallelism. So this picture is from registration here at CppCon Sunday evening. This is an example of effective parallelism. Multiple volunteers, each with a group of name tags for a group of attendees. It's not perfect because registration is sequential within each group. As you can see, 3 people lined up at the V through Z sign, V through Z table. But it's effective. 20 volunteers in parallel is faster than having a single check-in person, even if that person were the fastest check-in person in the world. This picture is from lunch on Monday. It's a not so effective use of parallelism. There are several payment terminals, but not enough to prevent long lines. At each terminal, paying for lunch has to be done sequentially, even though there's nothing inherently sequential about different people paying for their lunch. This could be better parallelized by having even more payment terminals, but that's probably not worth the money to set them up. And so this is the last discussion of parallelism in the real world. The rest of the talk will be about parallelism in C++. This talk is very code heavy with lots of code examples. If you prefer a more theoretical or philosophical talk, there's still time to go to Walter Brown's talk in Summit 8.9. A couple of assumptions underlying this talk. First, the vast majority of code cannot be effectively parallelized, but the gains can be tremendous when you have the right code. The biggest benefit comes from code that does the same computation over and over and over and over again on different data, where each little piece of that computation is independent of the others. You might have multiple threads running at the same time doing different things, but that's concurrency, as David Holman explained earlier this week in the Lazy Futures talk. That's not the parallelism that this talk is going to be focusing on. The second assumption is that you need the right hardware for parallelism to be effective. You need a GPU or a multi-core CPU. If the programs that you're working on will run on a single core CPU, nothing I say in this talk will be any use to you. So first I'm going to go over a number of different parallel programming models. So these are different ways that you can parallelize your code. This list is not comprehensive. There are other models out there that might be more effective for your particular situation, but these are some of the ones that I'm familiar with or that are used in the HPC environment where I work. For each of the models, I will show a very short code example just so you can get a flavor for what it looks like in the code. Later in the talk, I will have longer code examples with performance data for some of the models. There are several different strategies for parallelizing your code. They fall, I sort of see, into 3 main camps. Some of it, like OpenACC and OpenMP, do it through pragma directives in the code. That's how you express your intentions to the compiler. Other ways of parallelizing have language extensions, like CUDA and OpenCL. So these are actually changes to the language. You have to write non-standard code in order to get the compiler to parallelize your stuff. And then there are a whole bunch of libraries out there like Thrust and Kokkos, which look like C++ libraries. You include their header files, maybe link in their precompiled libraries. These libraries are, I think, always built on one or more of the other models underneath, but you interact with the library rather than with the underlying model. So here's the short example I'll show for each of them. This is the sequential version. There are 2 input arrays, x and y. Multiply x by a scalar, add that to y, and store the result in Z. Really simple. First model we'll look at is Pthreads. This was the original widely used threading library created back in the 90s as part of POSIX. It has a C interface. It's not designed for C++. So here's the Pthreads version of that example code. Because it's a C interface, we have to use pointers to functions. The function has to take a single void star argument and return a void star. We don't get to use lambdas. Since we don't have lambda captures, we have to marshal all the data explicitly to get it into our thread This is not the best model for C++. Don't use it, and it won't be mentioned again in this talk. In the C++ 11 standard, threads were added to C++. It's in many ways a C++ interface on top of the Pthreads functionality. When you create a stood thread object, it launches a new thread. The threads must be joined or detached explicitly, but don't ever detach them, always join them before the thread object is destroyed. And the thread, you have to manage the threads yourselves. C++ still does not have a standard thread pool or task manager to help you with your thread management.
Excuse me. What about task-based concurrency in the standard?
There's a little bit, there's async, there's
Right, exactly.
It's coming, I guess with coroutines you have some more, but that's more concurrency than the parallelism that we're looking at in this talk.
Okay. No, you mentioned there was no, you said something, there was no manager or something.
Okay, yeah, the comment is, yeah, I said that there's no...
I'm not challenging you,
Yeah.
I was just wondering what you would say about that.
The comment was the other, I said that there's no thread pool or other things for managing your thread. There's a little bit creeping its way into C++. It's more for concurrency rather than for the massive parallelism that we're talking about.
When you call async, it launches a thread in the standard model.
Right.
So it's not a cascading system. It's just like this.
Right.
So yeah, there's not good tools for managing your threads. So the example, here's the same example using C++ threads. It's much nicer than the Pthreads version. We launch the thread by creating a stood thread object, which we pass a lambda. Between the lambda's parameters and its capture, it's much easier to get the data we want into the thread. But it still takes some effort to manage the threads. We have to keep a container of the threads, and we have to join the threads at the end. If you switch to JThread, which is new in C++ 20, you can get rid of the explicit join at the end since JThread automatically joins in its destructor. But you still need the vector or some other container so that the JThreads have the right lifetime. OpenMP is a programming model for shared memory multi-core systems. It uses pragma directives to give your instructions or hints to the compiler. It's available in C++, C, and Fortran. More recent versions of OpenMP support doing your parallelism on the GPU rather than CPU, but the GPU capabilities aren't widely available in implementations yet. So here's the OpenMP example. It's about as simple as it gets. We add a pragma before the for loop. We're telling the compiler, we want you to parallelize this for loop. And it does all the rest. It creates the threads, it manages the threads, it takes care of destroying them at the end. OpenACC is a parallel programming model for shared memory multi-core systems and for GPUs. Again, it uses pragma directives to give the instructions to the compiler. It's available in C++, C, and Fortran. And because it targets GPUs, it also has directives for specifying the data movement. Remember, CPUs and GPUs have separate memory spaces, and so you have to worry about copying your data back and forth between them. So any GPU model will have ways of managing your data. So we look at the OpenACC example. We have a similar pragma just before the for loop saying, please parallelize this loop. But we also have the data directive. The first pragma, it says to copy X and Y to the GPU memory, and then when we're done, which happens at the end of the scope that the data directive is attached to, copy Z from the GPU memory back out. And that's what we need for this particular problem. When you compile OpenACC for multi-core CPU, the data directives are ignored because they're not needed in that environment. CUDA is a parallel programming model for NVIDIA GPUs. It uses language extensions and a library. And CUDA exposes more of the capabilities of the GPU than any other model. Here's the CUDA example. We have the special syntax. We have a global attribute on the function that we want it to run on the GPU. And farther down, we have the triple chevron syntax, which is used to launch the kernel, to tell this is where I want you to call this function on the GPU rather than CPU. So it has this special syntax that you need. Within your kernel code, there are magic variables so that you can identify the thread that you're on. And then it has the ways of doing the data movement. So we allocate memory on the device and move copy memory to and from the device. Next one I'll mention is Kokkos. It's a parallel programming model for performance portability on both CPUs and GPUs. It is a C++ template library. So you write your code against the library using templates. And it's built on top of a whole bunch of different backends, including CUDA, OpenMP, Pthreads, HPX, HIP, ROCm, SYCL, and there's a sequential implementation, and there's a couple more that are beyond that. Kokkos is open source and liberally licensed. So our Kokkos example, because it does support GPU backends, we have to deal with data with managing memory. Kokkos View both manages the memory in it and allows you to view your data in different ways. Deep copy is used to transfer the data. Kokkos provides several parallel algorithms, such as the parallel 4 that we use here. And the last one I'll talk about is C++17 parallel algorithms. I think they've been out enough, you've probably heard of them, know something about them, but essentially in C++17 defines execution policies. As of C++20, there are now 4 of them, and they're overloads to a whole bunch of the standard algorithms that take an execution policy. So if you want to run one of your algorithms in parallel, you pass it, say, the par execution policy as its first parameter. So the implementation status, where are these available? Intel came out with one of the earliest implementations, but they released it as a separate library. It's never been shipped with any compiler as part of a standard library. So all the algorithms are in a different names in the PSTL namespace, and it's based on TBB, or thread building blocks, which is a library implementation of parallelism that I haven't covered in this talk. Microsoft was the first of the mainstream compilers to ship an implementation so all the algorithms are available with the execution policy overloads. Of those, 39 of them have been parallelized, including all the most important ones: transform, reduce, and sort, and the scans, and for each, and reduce. 16 of them, they've decided it's probably not worth it to run in parallel, so they haven't done a parallel implementation of those, and 19 are still to be done. Others, libstud C++, which is under the GNU umbrella and ships with GCC. There's an experimental implementation of the parallel libraries available in GCC 9, but it depends on TBB, and it requires that you have TBB installed somewhere. libc++ is under the LLVM umbrella. It's the default library on Mac OS and is available with Clang. The parallel algorithms are under development. If you get their dev branch, there's an option you can pass to the compiler to make them available. They're sequential by default, but there is a parallel backend that is based on TBB. You'll notice TBB is mentioned here a lot. That's because libstud C++ and libc++ both used the Intel implementation as the starting point for their work, but neither of them has written a parallel backend that doesn't use TBB yet. Other sort of non-standard library implementations. Thrust is has a CUDA-based implementation for NVIDIA GPUs. Their implementation predates the C++17 standard. In fact, in some ways, it was the model for it. But because they built it before the standard, there's a number of differences between the Thrust implementation and the standard. It's in the namespace Thrust rather than STD. And because it's a CUDA-based implementation, you have to use a CUDA compiler to get the thrust. HPX is a library for all sorts of things for in the HPC and the high performance computing space. It includes implementations of the algorithms in the HPX namespace and has some extensions for the execution policies. You can configure them like attaching them to an executor or making them asynchronous. CppCon implements the parallel algorithms on GPUs if you feed it a custom execution policy. And at PGI, we have a project under development that I'm working on, which we hope to release in the first half of next year, if all goes well, where we will run the parallel algorithms, we'll run them on the GPU with the standard execution policies. And so, going back to the example with the parallel algorithms, our little one, we use the algorithm transform, we pass the execution policy par, means please run this in parallel. The inputs are x and y. The output iterator we send in is z, and the lambda has the transformation we do, which is a times x plus y. So that's it for the survey of programming models. Now we'll go through some bigger examples. There will be 2 code examples. I will show you the sequential code plus several parallel versions for each of the examples. I will show only the main loop, not the entire program. I will highlight the differences between the versions. And please do not try to understand all of the code. You'll fall behind and miss the main points. What I want you to pay attention to is how easy it is to write or read that code. I've spent some time optimizing the code, but I didn't try to eke out every bit of performance, because in this talk I'm looking for order of magnitude differences in performance, not that last 10%. The fine print on the performance measurements. All the measurements were done on a dual socket Skylake machine with a total of 40 physical cores and an NVIDIA Volta GPU, and more RAM than I could ever possibly fill up. The details about the compiler versions and the command line options I used are there on the slide. On to the first example. Traveling salesman. So the problem is a salesman has a territory, and in that territory has some number of cities, and he wants to find the shortest route that will visit every city. This is your classic NP-complete problem. There are no shortcuts to solving it. So the example code that I have is a brute force implementation that checks every single route to find the shortest one. So here's the sequential code. We have a function called findBestRoute. It takes a parameter, which is the distances between the cities, an array of distances, and the number of cities, and it returns the best route. Distances is really a 2-dimensional array, but since C++ doesn't handle 2-dimensional arrays very well, especially when they are dynamically sized and passed as parameters, it's passed as a 1-dimensional array. This will get better when MDSpan makes it into the C++ standard. Before we go on with the code, there's some helper code, which is the same for all the different versions. So route cost is a pair of route ID and cost. Default constructor constructs one with the maximum possible cost. And there's functions to compare them to see which is least costly. There's a regular function minf, and there's a function object called min. They do the same thing, but some cases we want a regular function, some cases we want a function object. Route iterator calculates a route. You pass the route ID and the number of cities into the constructor, and you call first to get the first city. You repeatedly call next to get the next cities in the route until done returns true. That's when you know you're at the end of the route. This is all the code for route iterator. Don't read it now. It's just here, so it's in the YouTube recording. You can read it there later if you're interested. So back to the code for the main loop. If there are n cities, then there are n factorial unique routes that visit all the cities. So we iterate over all the integers between 0 and n factorial. And for each route, we iterate through all the cities on the route, add up the costs of each of the hops between the cities. We compare the total cost of the route against the best route so far, and when we're done, we return the best route. Okay. Before moving on, I want to look at this code a little more closely. The green code is easily parallelizable. It doesn't depend on any iteration. It's local there. It doesn't write to any variable outside the loop. You will see this exact same code in all the different versions of this problem. The code in red is the problematic code. It writes to a variable that's outside the loop. So if we were to parallelize this naively, we would run into race conditions and have problems, and it wouldn't work right. So this is a reduction where we are looking for the minimum value among the set of all the costs. And getting that code to work is where all the effort will go in the parallel versions. This is not a very interesting graph because we're not comparing different versions. I want to introduce the graphs. All the graphs will show speed up against a reference implementation. So taller means faster, smaller means slower. Green bars were compiled with the PGI compiler. Purple bars with GCC, and blue bars, which will come later, were compiled with NVCC, which is the CUDA compiler. The reference implementation for this problem is the sequential code compiled with the PGI compiler, which took 22 minutes, 40 seconds to calculate 6.2 billion possible routes between 13 cities. The GCC version was a little slower, taking 27 minutes, 41 seconds. So now on to the version Traveling Salesman that uses C++ threads to run it in parallel on the CPU. So first, we ask the implementation how many threads it thinks it can support by calling hardware concurrency. We have a container to hold the thread objects. We add the threads to the container as they are created. And then at the end, we join all the threads. That's how the main thread knows that they are done. Each thread keeps track of the best route found by that thread. At the end of each thread, use a mutex to update the overall best route. This lock is only acquired at the very end of the thread, not in each iteration, so there should be little or no contention. And so we run this. PGI compiler is 43 times faster. The GCC version is 30 times faster. These are sort of within the ballpark of what you would expect on a machine with 40 physical cores. The OpenMP version. This code is identical to the original sequential version, except for the 2 additional pragmas. This takes advantage of OpenMP's user-defined reductions. So the first pragma defines the reduction. It tells the compiler how to find the minimum of the root cost objects. And then the second pragma, we put on the loop, it says, please run this in parallel, and there's a reduction inside the loop that fits the one that I just defined. So those are the instructions to the OpenMP compiler. The PGI's OpenMP implementation does not support user-defined reductions, so I only have results for GCC. And here it's a little bit faster than the GCC manual threaded version, 32 times faster than the sequential. OpenACC doesn't have user-defined reductions, so the code needs to be changed to do the reduction manually, which frankly is a pain. The first highlighted pragma specifies the number of threads to use, which is not recommended practice for OpenACC. That's normally left to the compiler. Lower down, to manage all those threads, the main loop is broken into 3 nested loops. There's a temporary array to hold the best route for each thread. When all the GPU threads are done, the CPU looks through the data structure to find the best overall route. As I said earlier, OpenACC can be compiled either for multicore CPU or for GPU. So the bar on the right is ACC for CPU for multicore. It's similar to the other multicore runs. When we compile for the GPU, things get a lot faster. Runtime is down to 1.25 seconds, down from our original 22 minutes. In Hannah's compile time regular expression talk on Wednesday, she showed a 100-fold speed up over C++ standard regular expressions. Here we have made the code 1,000 times faster. Though I cheated by changing the hardware, switching from a CPU to a GPU. I still think Hannah's speed up is more impressive because she did it on the same hardware. This is the CUDA, or this is part of the CUDA code. And this is the rest. I won't try to explain it all, but I do want to point out how the reduction happens. It's broken into 4 different steps. First, each thread keeps track of the best route for just that thread. Second, all the threads in the warp work together to find the best route for that warp. Third, one of the warps gathers the best route from all the other warps, finds the best route for the block, and stores that in a temporary array. And finally, the host code goes through the best route from each block to find the best overall. That's a lot of code to add to your program to get it on the GPU. But it sure runs fast. So we're down to 1.1 seconds. Because Kokkos has GPU backends, we have to use Kokkos view and Kokkos deep copy to manage the memory. I want to point out there's very little memory for this. Just the distance array takes up only 676 bytes, so it'll fit in the cache, but we do have to worry about how to get it to the CPU. So we have the view and the deep copy here. We use the parallel reduce algorithm, and Kokkos has a reduction operation that keeps track of both the value to be minimized and an identifier, which is exactly what we need for the traveling salesman. So we threw away the root cost class for this one and used Kokkos's min-lock reduction directly. Kokkos has many backends possible. I'm going to show you results from the OpenMP backend and the CUDA backend. So the bar on the right is for OpenMP. The graph is scaled so you can better see the CPU results. And the Kokkos OpenMP is on par with the other CPU multi-core runs. Now let's add the results for the CUDA backend. 390 times faster is normally a great result, but it's several times slower than the other GPU results. So I talked to the Kokkos developers. They pointed out that Kokkos is, by default, it's tuned for typical scientific applications, which have a lot more memory access than traveling salesmen. So the Kokkos developers sent me a patch, which is actually was just this week, was released in Kokkos 3.0, so it's available, and gave me and told me how to give hints to the Kokkos scheduler. So the text in red shows the change from the previous run, and this configures the policy that we're passing into parallel reduce, giving the hint that the algorithm is computation heavy. The work item property hint heavyweight. So when using this version, the Kokkos CUDA backend now performs as expected. So the final version for traveling salesman uses the C++17 parallel algorithms. So our function is now a single call to the transform reduce algorithm with the parallel execution policy. The input is a sequence of integers from 0 to n factorial. Counting iterator is a helper class that really should be in the C++ standard, but you can get it from Boost or Thrust or various other places. Counting iterator makes it look like you have a container full of consecutive integers without having to create an actual container. This is the initial value for the reduction. Root cost min is the reduction function. In this case, we want the function object, not the regular function. And this lambda is the transformation function. It converts the integer, the root ID, into the cost of that root, or actually into a root cost object. So once you're familiar with transform reduce, this code is at least as simple as the original for-loop version. If you watched Connor's algorithm intuition talk on Monday, you will understand the importance and the beauty of transform reduce. So we can compile this code with GCC 9.2 to run in parallel on the CPU. So it is 33 times faster than our sequential version and similar to most of the other CPU multicore versions. We can also compile it with the PGI, with the development version of the PGI compiler, so it'll run that same code with the parallel algorithm on the GPU. So we're down to 1 second flat to compute 6.2 billion possible routes between 13 cities, 1,355 times faster than the sequential version, with code that is clear, portable, and standard. So on to the next example. This is a very common example in the scientific computing community. Jacobi Laplace heat transfer thingy. I've seen a bunch of different names. I'm not sure which name is most often used. The problem statement. Given a metal plate or some other two-dimensional object where the temperature of the edges is known, calculate the temperature of the interior. Laplace refers to the math equations that sort of model the system, and Jacobi refers to the method of solving those equations. So the algorithm that we will use represent the metal plate as a two-dimensional array of temperatures with constant temperatures on the edges. Simulate the heat propagating through the plate by changing each interior point to be the average of the temperatures of its 4 surrounding points. And then we keep iterating. We keep doing step 2 over and over again until the temperature change from one iteration to the next is below a certain threshold. So here's the sequential code. We have a function called Jacobi solver. It takes data as an input, which is an m by n two-dimensional array, and it takes our threshold, max diff is our threshold that we're looking for. So when the changes are less than that, then we're done. It returns the temperatures of the plate back through the data. So it modifies the data array in place and returns the number of iterations that it took before it converged. We need to allocate a second array and copy the data into it. Only the edges are important, but it's easier to just copy the entire thing. Then the main body, we iterate over just the interior points. So you notice the index goes from 1 to m minus 1 rather than the usual 0 to m. And then we set each point to the average of the surrounding points. And at the same time, in the same loop, we check how much the value changed and see if it was greater than our threshold. Sorry. At the end of each iteration, swap the pointers to the two arrays. And if any value changed more than the threshold, keep going and do that iteration, do the next iteration. Once we're done iterating, if the last iteration that was run wrote to temp, then temp needs to be copied back to data, because data is how we're returning the result to the user. If you recall Andre's keynote about optimizing sort, he said his advice included avoiding branches in inner loops and to break out of loops early wherever possible. This code does not follow those guidelines. We can avoid those pitfalls by changing the code to have two separate loops. The first one does the transformation. It doesn't have any branches in it. The second one checks the threshold and breaks out with a goto as soon as possible. I said at the beginning I don't care about 10% performance changes, but this little change is much bigger than that. When compiled with GCC, this is 30% faster. When compiled with PGI, it was almost twice as fast. I'm not entirely sure why. My guess is that by taking the branch out of the loop, it allows the compiler to much better vectorize that first loop. So again, this isn't very interesting because it's just one performance model, but it's the same thing. Green is PGI, purple is GCC, blue is NVCC. So for the sequential, it took 4.5 minutes for a 12,000 by 8,000 array, which took, I set the threshold, so it took 3,891 iterations to converge. And this time GCC was a little bit faster than PGI, so it's our reference implementation for this example. The OpenMP version, mostly we just add pragma OMP parallel 4 to all the loops, except for the one that checks against the threshold. OpenMP does not allow you to jump out of the loop, so we can't do an early exit. Instead, we mark the loop as a logical OR reduction. For the sequential version, it was much faster to have iteration code in separate loops. For OpenMP, it's exactly the reverse. If we combine the code back into one loop, which has a logical OR reduction, compiled with GCC, it's 35% faster, and PGI is 25% faster. So this example proved a lot more interesting from how to code it up and how to optimize it. So here's the performance of the OpenMP. GCC did a lot better. It's 11 times faster than the sequential version. With traveling salesman, we saw speed-ups between 30 and 40 times for the multi-core CPU versions. This time we're only seeing 11. And the difference has to do with the memory usage. Traveling salesman used 676 bytes of memory. This one uses about 800 megabytes. That is where you access all 800 megabytes each time you're doing an iteration. So there are cache issues here. We could probably improve things by changing how we access the cache and the order and things, but that was beyond what I was, the scope for this talk. The OpenACC version, similar pragmas on the loops, except we added collapse 2, and that tells the compiler to take the 2 for loops and iterate them over in just one box, basically collapse them into a single loop. The 2 loops are more clear in your code as you're writing your code, but the compiler can parallelize it better if you have a single loop. So this is telling the compiler, basically getting the compiler to do the hard work, which is what you want. OpenMP also supports a collapse clause, but for reasons that I don't know, I didn't try to figure out, when you put collapse 2 on the OpenMP pragmas, it actually got a lot slower. With OpenACC, it gets noticeably faster. Because OpenACC can be compiled for the GPU, we have the data directives. We need data directives to manage our movement of our data. This one says to copy data to the GPU at the beginning, and then at the end of that scope, copy data back, which is what we want. The temp array is only used on in the device code. We don't ever need it on the host, on the CPU. So that one has a create clause, which tells the compiler, just make sure this memory is there on the GPU, but don't ever copy it. So the performance for OpenACC. Remember, we can run this on either CPU or GPU. CPU version was 7.4 times faster than the original sequential. When we run it on the GPU, it's down to 5.4 seconds, which is 51 times faster than our sequential. So not 1,000 times faster, but still pretty good. I'll take 50. Kokkos version. The Kokkos policy for a parallel 4 can iterate over 2 different indexes. So we specify down at the bottom, see in the very last row, we specify from 1 to 1 up to m-1, n-1. It handles that. And these indexes don't have to start at 0. So that was nice. Kokkos view can also provide a 2-dimensional view over your data. So that makes our indexing, our math on the indexes into the arrays simpler and more clear. And how does it perform? Again, I'm showing the OpenMP and CUDA backends for Kokkos, which are a little bit slower than the other ones in our model. I have two caveats for this. One, when I ran these Kokkos runs, the test machine wasn't completely idle, so the actual numbers are probably a little bit better. I don't know exactly how much. And two, this was the last addition to this talk. It came in just yesterday. So I haven't had time to fiddle with it, and either me or the Kokkos developers haven't had time to fiddle with it and see. There might be some small changes that could get 2 or 3 times faster, like we saw for traveling salesman, but I just haven't had time to investigate that yet. And finally, the parallel algorithms version. We can use parallel copy at the beginning and end when we just need to copy the whole array. For the main body, we use transform reduce. So as Bryce mentioned here at CppCon 3 years ago, and as Connor mentioned earlier this week, transform reduce is the most important standard algorithm. You can do it to solve all sorts of things. We used it to solve both the traveling salesman and Jacobi. Our input is, again, using counting iterator again. We iterate over all the indexes, but we can skip the first and last rows since those are constant. We don't want to change those. We have a logical reduction with initial value of false. Sorry, logical OR reduction. What's the OR reduction? Because we are using a single index, the math to index into the array is a little bit different, and we need to skip over the first and last entry of each row because those are edge nodes that we don't want to change, so we have to do a mod n and see if we're at the first or last entry. So far we've gone back and forth about whether it's faster to combine the 2 loops or to keep them separate. You would think that since the combined loop was faster for all the other parallel examples, it would also be faster for parallel standard algorithms. But no. For reasons I can't explain, separating the code into parallel for each and parallel any of is about 10% faster. So this is the one that I did the performance results on. Again, with GCC 9.2 compiling for multicore CPU, we get a pretty good result, 6.8 times faster in the range of all the other multicore CPUs. And using the PGI compiler for the GPU, got 37 times faster. That's good, though not quite as good as OpenACC. So this one we have some more variety in the scale of the range of our performance results. So before I get to the conclusions, I want to give some thanks to people who helped me with this talk. Christian Trott and David Holman from Sandia helped with the Kokkos. Louis Dion updated me on how libc++ implementation is going. Billy O'Neill informed me about Microsoft's status. Gordon Brown helped me with SYCL. And then Matt Colgrove, my coworker at NVIDIA, wrote the OpenACC versions for both of the main examples. And Daniel Tien, my coworker at NVIDIA, is my partner in crime on implementing the parallel algorithms in the PGI C++ compiler for the GPU. And we would like to make this team of 2 be more, so we are looking to hire more people to work on our PGI compiler. So if you want to do C++ compiler work, contact me or Bryce or anyone else at NVIDIA. So, in conclusion, first, parallel is faster than sequential. If you have code that is safe to run in parallel, I encourage you to try it out. Try out one of these models and see how much faster you can get it. 2, parallel on the GPU is faster than parallel on the CPU. So if you have a GPU handy, try it out. See what performance differences you get. And then finally, in my opinion, the C++17 parallel algorithms have good performance versus readability trade-offs, which means you can get good performance without having to sacrifice clarity, maintainability, or portability once implementations are more widely available. Thank you.
Hi there. Can you go back to your first transform reduce example? Or really any of them that have counting iterator in them?
Okay.
Sure. So are you aware that there's UB in this example? And if you are, have you filed a defect report so that we can fix it?
No. What's the UB?
So the parallel algorithms require forward iterators in the standard, and counting iterator is like a stashing iterator. Like it doesn't.
No, I made it. It's a random access iterator.
It doesn't, like you can't store an address to the number, increment the iterator.
Oh, that's right. Its reference type is not quite correct.
So have you submitted a defect report to make this work? Because I agree it should work.
No, I have not.
Please. Thank you.
Okay.
Yeah, so the order of magnitudes are such that I don't know how meaningful the difference is, but I'm just curious, how do you normalize the performance of the GPU you're choosing and the CPU? Is it based on cost or?
What do you mean by normalize?
Well, so you could get the cheapest CPU you could find and the best GPU you could find. How do you make that so it's kind of a comparison where you can?
I haven't tried to do those computations or figure out exactly what variables you would measure off the top of my head. It depends on how much code you can get to run on the GPU. A lot of applications, most code out there, like I said at the beginning, most code out there is not parallelizable easily. Mm-hmm. If your code has very little on the GPU, then you want to put all your money in the CPU. If you're a massive scientific simulation where you can run everything on the GPU, that's where you're going to put your money. So I think it'll depend on your application.
All right, thank you.
Thanks for the talk. Have you ever measured the performance across multiple GPU?
No, I have not. This was all single GPU.
Thank you.
Yeah, very interesting talk. So what would I do if, say, I wanted something like the FFT, which isn't in a standard algorithm? Would I have to use like FFTW on the CPU and then do something else for the GPU to take advantage of that common code using the PGI compiler?
Are there GPU versions of FFTW?
No, I don't think so.
Okay.
It's CPU only. So I was asking, how would you kind of handle that? Like, you just want to do an FFT and make it choose, I guess.
It's a complicated question. Actually, the person sitting across from me has worked some on FFTW in that domain. There are people in my office who can answer this much better than I can. But you would have to, if there's no GPU version available, probably have to bug the people who maintain the libraries and get them available. I'm sorry, I don't have a good answer for that.
Hello. The question is whether you can see an easy way to run parallel algorithms in parallel, so that, say, you have a partially shared data and would like to parallelize the parallel parts also to utilize your hardware better.
Taking a parallel algorithm and invoking another parallel algorithm within it is many, many times harder than just getting your parallel algorithm.
So in CUDA, there is a way to specify a flag to get a default
Yes, in CUDA, it's possible to launch new kernels from within your device kernels.
No. I'm not talking about dynamic parallelism.
Yeah, but people don't. That's not widely used. And
No,
it's not
I'm saying that there is a flag for compiler to give you a default stream per CPU thread. So in ACC, I haven't found such an ability and had to explicitly specify asyncs and then introduce synchronization by hand.
Okay. People have had success doing parallelism on the CPU and then having each of those threads invoke parallelism on the GPU by having OpenMP for the CPU parallelism and OpenACC for the device parallelism.
Right, but they utilize the same stream by default.
That I'm not familiar enough with the details of how that works and the complications of that. But in general, nested parallelism is very hard. It's much harder than your regular single level parallelism.
Thank you.
Hi, David. Thanks for including us in this study, and thanks for the talk. So I noticed, looking at your examples, trying to compare complexity and readability, that a large part of the difference, at least in my mind, for both OpenACC and Kokkos was the explicit memory management. But either of those models would have worked just fine with unified memory. It's just that those models also support non-unified memory, and so if you want to be generic over that, you have to write the extra stuff.
Yes.
But the question that's associated with this is, if you were to add in the explicit memory management requirements to do non-unified memory in the parallel algorithm case, do you think that the readability would be a little bit more on par?
Yes.
Okay.
So let me, as David pointed out, there are advances in memory management for GPU programming. Unified memory gives you at least some, like right now it's the heap. The heap is shared, the CPU and GPU have the same virtual address space for at least part of the memory, often what's on the heap. And the OS and device drivers will take care of moving the memory automatically, and you don't need your explicit data movement directives. So yes, the models that have explicit data movement would be easier if you can get all your data into the managed memory. And the parallel algorithms would become more complex if you had to explicitly specify data movement. So yes, that is a valid point.
Thank you.
Excuse me, one more question. Whether you have an explanation why pure CUDA implementation showed worse performance rather than for example,
because I am not a CUDA programmer.
Okay.
And I wrote it myself, and I didn't spend time trying to optimize it much. I know specifically that final loop of going over the array to find the best route at the end that's done on the host, it would be faster if I moved that to the GPU. That's one example of where I could improve the performance in the CUDA example.
Thank you.
But yes, I would expect the CUDA version, if I spent time optimizing it, or got a CUDA expert to spend time optimizing it, I'm sure the straight CUDA example could be at least as fast as any of the others. Anything else? Okay, thank you very much for coming.